Arithmetic involves only four basic number operations: addition, subtraction, multiplication, and division. But today, we'll talk about mathematics, not just arithmetic. We have more complicated number operations in modern day mathematics. We can trace all of them back to arithmetic. The implication, therefore, is that arithmetic grew into mathematics. Mathematics contains more than these four basic operations, but are still an extension of these four. How did arithmetic turn into mathematics that we know today? That takes us to the fifth lesson objective of this topic: how arithmetic became mathematics. Please listen. In this section, we pay attention to how arithmetic became mathematics. Earlier, we learned the meaning of arithmetic. We also mentioned mathematics, and I believe that that was also understood. But in this section, we want to know how this arithmetic grew into mathematics. Mathematics is an advancement over arithmetic. This write-up summarizes how. And afterwards, we intend to use two examples to show how arithmetic became mathematics. It says, many factors combine to determine how our life runs. Both natural and man-made systems control our life. These factors that determine how our life runs do so through these systems. These factors combine in the manner of basic accounting, from simple addition to very complex number operations. Advanced number operations having their root in the arithmetic of accounting form the modern-day mathematics. For easy understanding, let us use two man-made systems to illustrate how arithmetic is capable of becoming mathematics. The first is the case of printing recharge cards, telephone recharge cards. Let us see. As we can see, example 1 is about printing recharge cards. It says a recharge card developer wants to produce recharge cards from a 4-digit number, which is 7235. That is, he wants to use these 4 digits to print different recharge cards so that each recharge card has its own set of numbers, and all the numbers that are on that recharge card are gotten from these 4 digits. The difference lies in the arrangement. We know that 7235 is not the same thing as 2735, and it's not the same thing as 3572, and so on and so forth. It means that this 7235 can be arranged in several ways, so that each way it is arranged is a recharge card on its own. So we now ask, how many cards can he produce using these 4 digits? That is, in how many ways can he group these digits? That is, can he group 7235 so that each group that makes one card differs from one another or differs from others? The answer lies with factorial. What is factorial? Let us illustrate with this 4-digit number. We continue. The number of recharge cards from 7235, which you can print from this 7235, is equal to 4 factorial. This is not 41. See 4. See this slash and a dot under it. This is not 41. It is read as 4 factorial. 4 factorial. What does 4 factorial mean? It means 4 times 3 times 2 times 1. When evaluated, 4 factorial, which is equal to 4 times 3 times 2 times 1, is equal to 24. That is 4 times 3 is 12. 12 times 2, 24. 24 times 1, 24. What does this figure mean, 24? What does it mean? It means that he would be able to arrange 7, 2, 3, 5 in 24 ways, 24 different ways. That is, we can obtain 24 recharge cards from 7, 2, 3, 5. Each arrangement will correspond to one recharge card, and each arrangement will be quite different from other arrangements. What it means is that he can get 24 recharge cards from just these 4 figures. Since 7, 2, 3, 5 can get us just 24 recharge cards, that is not economically viable. If it had been only 7, 2, 3, a number that contains 3 digits that was used to create these cards, that would have been 3 factorial, and that would have been just 3 times 2 times 1, only 6 recharge cards. The implication, therefore, is that they had a number of digits in the number chosen. They had a number of recharge cards we can print from them. No wonder in today's world, we have several digits in a number assigned to a recharge card. That is because its factorial will be a large number. Could you imagine what the result will be if this is a 12-digit number and you want to create recharge cards from such a number? That would be a large number of recharge cards. Before you finish printing the recharge cards, you know how many you would have gotten by then at the end of 8. So far, this is just for simplicity. From 7235, the developer of recharge card will print just 24 recharge cards by arranging these numbers in different orders. Now, let us see in 24 ways we can arrange this 7, 2, 3, 5. Watch out. These 24 arrangements are the first number, the first 4-digit number, that is 7235, see it here. Let it be the first recharge card, that is 7235, which means on the first recharge card, what will be printed will be 7235. Second recharge card, what will be printed will be 7352. Then next, 7523. Then we have 2735, 2357, 2573, 3725, 3257, 3572, 5723, 5237, 5372, 5327, 5273, 5732, 3275, 3752, 3527, 2753, 2537, 2375, 7532, 7325, and 7253. How many are they? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24 recharge cards, which means we are correct when we say that the number of cards to be printed from this 4-digit number is 24 recharge cards. Why are we interested? Don't forget that we are talking about arithmetic being the root of mathematics. This is no longer simple arithmetic. It is now a continuous multiplication. Watch this expression, please. 4 times 3 times 2 times 1. And this is called 4 factorial. Therefore, factorial is a sort of secondary arithmetic operation. No longer can we call it just ordinary arithmetic. It is now mathematics. Therefore, factorial, which help recharge card printers to print codes on the cards, is actually mathematics, having its root in arithmetic. The second example is connected with roofing a house. We have it that the same wall plate angle could be used to roof both small and bigger houses. Let's use this sketch to illustrate what I mean. Take a look at this sketch. I employed this to represent in real life what we usually see when roofers want to start roofing a house. They construct what looks like this. That is the sketch of roofing a house. It means that this is a small house to be roofed, and later, let this be a bigger house to be roofed. Do not lose the sight of the fact that this angle, theta, is what we refer to as wall plate angle. This, for this small house, is the initial rafter crossing, and this point corresponds to the center of that rafter. From here to here corresponds to the height of that proposed roof. Then, to connect both ends, this long rafter is to be placed. So for this building, this dotted line tells us how the sketch will be when completed. But for our case here, we're going to make use of this half, this left-hand side half of this sketch. What's the point here? The point we want to make is that a roofer should know that for roofing this small house and roofing this bigger house, the same angle can be used. What it means is that the same wall plate angle, theta, can be used to roof both a smaller house and a bigger house. Why? Soon we find out that ratio of these sides, the ratios of these sides remain constant irrespective of the size of the house, as long as this angle remains constant. This was a striking discovery made in the past. Afterwards, we state why we are saying this at this point. Don't forget that this is in connection with arithmetic and how it became mathematics. Let's go on. Again, going to this smaller house. The height is 4 meters. Half of the length of the rafter, initial rafter crossing, is 3 meters. And from this end to this end is 5 meters. The roofer or the engineer is to use a protractor to check the angle that this theta is and keep record of it. Whatever it is, he keeps record of it, but he has gotten the shape of what he is looking for. Now, let us look at the ratios of these three sides. First, before we proceed, let me inform you or remind you that this is a right-angled triangle with angle 90 here. When tested, we take the ratio of 4:5, that is 4/5. When converted to decimal, what we have is 0.8. This ratio of the height to this longer side became known as sine. Therefore, we say that sine of this angle is equal to 0.8. What does this information mean? It simply means as long as this angle is constant without changing, that this height over this length is equal to 0.8. Even if this 4 changes and this 5 changes and this theta does not change, what it means is that at the end, whatever the 4 has become over whatever the 5 has become will still give us 0.8 as long as this theta remains constant. That is the information. What about the next one? 3/5. That is this half length of the rafter over this length. That is 3/5. It is equal to 0.6. Also, what it means is that as long as this 3, as long as this angle remains constant and this 3 changes to whatever length it will be, and this 5 turns to whatever it is going to be, to make another right angle triangle, as long as this angle here did not change, whatever 3 has become over whatever 5 has become will still give us the same 0.6. The ratio of this side to this side became known as cosine. That is why we say that cosine of theta is equal to 0.6. What does that mean? It means that as long as this theta is concerned, as long as it remains constant, any ratio of this side to this side, no matter what the sizes would be, will always give us 0.6. That is information. Similarly, this side over this side will give us 1.3, and that ratio is called tangent. That is why we conclude that tan theta is equal to 1.3. Now, these ratios 0.8, 0.6, and 1.3 approximately are applicable to this small house. Keep these ratios and then try to reinvent them or reemploy them when trying to consider the dimensions of this bigger house. Again, take a look at this bigger house. What did you observe? Personally, I observed that this bigger house is twice this smaller one. How did I know? Check the height from here to here for the small house. And for the big house, check from here to here, which is the height. This is 4 meters, and this is 8 meters. 4 times 2, that is twice 4, give us 8. What about half of the rafter crossing? It was 3 before, and now for the bigger building, it is 6. That means from 3 to 6, it is still twice. What about this crossing? It used to be from here to here, 5 for the small building, and now it is from here to here, 10 for the bigger building. That means 4 became 8, 3 became 6, and 5 became 10. What it means is that this bigger house is actually twice the size of the smaller house. Let us look at the ratios of the sides, one of the 2 sides of the sketch for this bigger house. Again, let us look at this part of this bigger house. Let's suspend this right-hand side and focus on this left-hand side of the bigger house. That will be going from here. It runs this way and like this. What then will it be? Let's again look at the ratios of the 3 sides. Also, with respect to this bigger house, we see that if 4 over 5 gave us 0.8, 8 over 10, that is 8 over 10, also give us 0.8. Also, in the smaller house, this 3 over 5 give us 0.6. Therefore, 6 over 10, that is 6 over 10 here, also give us 0.6. And in the smaller house, 4 over 3, that is 4 over 3, give us 1.3. Likewise, 8 over 6, 8 over 6 also give us 1.3. What a wonderful correspondence. The implication is that the same wall plate for building a small house, wall plate angle for building a small house can be used, that is multiplied according to a ratio, to roof a bigger house. It does not mean that at each time when building a bigger house that the ratio must be that of a whole number. That is, the factor that multiplies the size of the house must be a whole number. That 4 became 8 with a factor of 2, and 3 became 6 with a factor of 2, and 5 became 10 with a factor of 2 is never compulsory. Somebody could like to build a house that is 1.5 times as big as this smaller house. At that point in time, the factor is 1.5, not 2. Any factor at all can be used. But as long as this angle is constant, no matter the factor, whether it's a whole number or a decimal or a mixed number that is used as a factor for multiplying the size of the smaller one, as long as this angle is constant, that practice is valid and is going to give a correct translation of a small house into a bigger one. Therefore, as long as the wall plate angle is the same, we can use the angle we used to construct a small house to construct the roof of a small house to construct the roof of a bigger house. With all this I've been saying, there is just one point I want to drive home. What is it? When you hear sine, what comes to your mind? What comes to your mind is mathematics. You hardly remember arithmetic. When you hear cosine, what comes to your mind? The same thing. Tangent, the same thing. In fact, if you hear sine or cosine or tangent, you start thinking about, if you hadn't experienced something more complex than what you've known before, that is pure arithmetic. But hardly will you know that it is just an application of arithmetic. Just watch how this sign came to be. It came from just a division. When 5 divides 4, we have 0.8. Division is pure arithmetic. And all the ratios here, the sine, the cosine, and the tangent, are all divisions. 4 over 5, 3 over 5, 4 over 3. They're all divisions. Therefore, this thing, which is division, which is arithmetic, has put on a new name, which is studied in pure mathematics, especially in connection with geometry, as we just had it here.